In this video we describe how to derive the Henderson-Hasselbalch equation and how to apply it to calculate pH in buffer solutions. Let's consider here the dissociation of a weak acid, which is going to be generic, HA, into protons and the conjugate base. Right, this is all dominated by an equilibrium constant K sub A, which is the concentration of protons at equilibrium multiplied by the concentration of the conjugate base over the concentration of the weak acid. And one of the things that we could do here is try to calculate what the pH of the solution is. Until now, the way that we have solved these problems is by working through an ice diagram in which you start with initial concentrations and then look at the changes and then find the equilibrium concentrations and then solve for generally a quadratic formula to find what the pH is, the concentration of protons, and then the pH is. But it turns out that there's an easier way to do this, which is avoids entirely the Henderson-Hasselbalch equation, the ice diagram, which is called the Henderson-Hasselbalch equation. All right, let's see how that works out. Right, notice that somehow the pH is actually buried into that expression, and we know that the concentration of protons and the pH are related by a base 10 logarithm. So the first thing that we can do here is take the minus base 10 logarithm of that expression and see where that leads us. Right, so we do the minus base 10 logarithm to both sides, K sub A, and then we have here the minus base 10 logarithm of those concentrations. Great. Now that is the logarithm of a product, and what I'm going to do is separate this product into protons and then the ratio of the conjugate base over the weak acid. Okay, so the logarithm of a product is the sum of the logarithms. So what we'll have right here is minus base 10 log of K sub A, and then minus parenthesis base 10 log of the concentration of protons plus the base 10 log of the concentration of A minus over HA. Okay, great. Now, interestingly here, what we have is that we can operate, right? So that's going to give us some minus there, and then a minus there. Okay, and we can clearly recognize here familiar terms. That is obviously the pH, and that is what we call the pK sub A, which is the minus base 10 logarithm of the equilibrium constant. So pK sub A is going to be equal to pH minus the base 10 logarithm of the concentration of the conjugate base over the concentration of the weak acid. We can rearrange this expression to come up with the Henderson-Hasselbalch equation, which is this one. And the goal of this is to be able to calculate the pH very quickly. Okay, so that will be your Henderson-Hasselbalch equation. Now there is something that is, you can use this equation for any type of weak acid dissociation, but there is something that is very special about when you apply this to buffers, which simplifies the equation tremendously, right? So suppose that we start here with a buffer, which is going to have a concentration of 0.1 molar of this acid and 0.1 molar of this base, right? So these are equal and high concentrations of the weak acid and the conjugate base, and that means that you're going to have some buffer action here. So if you go through the ice diagram for this process, ice, right, you will get to something that looks like this: 0.100 minus x, and then 0.100 plus x. Right? The idea here is that now you can try to plug this into the equilibrium constant expression. Those will be the concentrations at equilibrium, right? And then what you always find when you have these buffers is that x is very small, so then the concentration of the weak acid is the same as what you had initially because x is very small, and the concentration of the conjugate base is exactly the same as what you had initially, right? So you can codify that as saying that if you have a buffer, the concentration of HA at equilibrium is exactly the same as the concentration of HA initially, okay? And then the same thing will happen for the conjugate base. The concentration of conjugate base at equilibrium is exactly the same as what you had initially, what you put in the pot. And again, you can now take these terms and bring them back to the Henderson-Hasselbalch equation, and this makes the calculation of pH straightforward, right? Because now what you can do is say, well, that is going to be equal to pK sub A plus based on logarithm of the concentration of the conjugate base, what you put in the pot, and then this one as well, the initial one, right? So the calculus is now going to be trivial again for buffers, right? So we can actually calculate what the pH here would be for this particular buffer. Notice that what you have here is that this is exactly the same initial concentration of conjugate base and weak acid. So that is the based on logarithm of 1, which is equal to 0. What that means is that the pH, when you have equal concentrations of the weak acid and the conjugate base, is exactly identical to pK sub A. Okay, so we can actually do then a numerical example to illustrate this. We can then take this and make it hydrofluoric acid. And hydrofluoric acid has a K sub A of 7.2, 10 to the minus 4. Right, when you do that, come to this expression, and this happens to be 3.14. Okay, the pH is going to be equal to the pK sub A. Okay, so again, this is an illustration of the Henderson-Hasselbalch equation after we have derived this. Now, to further illustrate how useful this expression is, what we can now do is add a little bit of base to see how the buffer responds to that addition of base, and you will see that the recalculation of the new pH after we have added the base is also straightforward, okay, with the Henderson-Hasselbalch equation. Right, so we have this, and then the idea here is that from this buffer now we're going to be adding a little bit of base, so 0.010 moles of sodium hydroxide. And the question would be, what is the new pH after you have done this? Right, so what you do is write here the equation for the acid-base reaction. Right, the base will react with the weak acid to generate sodium ions, fluoride, and then water. So we're going to write here the concentrations before the base is added, before reaction. Actually, we're not going to work with concentrations. We're instead going to work with moles, because this is now a stoichiometry problem. Okay, suppose that we have 1 liter of this buffer solution, right? So 1 liter, 0.1 molar, that is going to be 0.100 moles of the acid. We're adding here 0.010 moles of the base, and then initially we also have some fluoride, and the amount of fluoride that we have is 0.100 moles. Okay, so after reaction, the base will be completely consumed, and hydrofluoric acid, about 10% of what you had, has reacted with the base, so the only thing that is left over is 0.090 mole. And then 10% more of the conjugate base has been generated. Okay, so that is the stoichiometric calculation for the reaction between excess acid and then a little bit of base. Now, so those amounts of weak acid and conjugate base have changed, and now you simply have to recalculate what the molar concentrations would be to go back to your Henderson-Hasselbalch equation. Right, so the volume is 1 liter, and we're going to assume that we have added so little base that the volume hasn't changed appreciably. Right, so what that means is that now my concentrations of HF before I start the equilibrium will be 0.090 molar, and then the concentration of fluoride before this equilibrium takes place, that is going to be equal to 0.110 molar. Okay, so there's that. We can then come here and calculate what the pH is going to be. Now this term is not going to be 0, instead it's going to be log of 0.110 molar over 0.090 molar. Okay, and that gives you a pH of 3.23. So yes, the pH has increased, but only a little bit. Okay. Again, this illustrates quite nicely how useful and straightforward it is the use of the Henderson-Hasselbalch equation.